everyone. We are going to be talking about social spider algorithm from nature inspired learning. What is nature inspired learning? Nature inspired learning in simple means solving problem based on the natural phenomena, that is nature phenomena. As we know, it is a solving problem by evaluating from the strategies from the nature. Now, in order to understand social spider algorithm, we need to understand some key concepts such as swarm intelligence, meta heuristics, evolution, and applications. Now, meta heuristics are nothing but the high level procedures for solving complex optimization problems. Evolutions, nothing but the algorithms inspired by natural selection and adaptation. Applications are nothing but we can implement all these algorithms, all these strategies in engineering, concept, design, data, everything. Moving on to social spider algorithms. We have here the social spider algorithm. The inspiration is directly taken from the social spider behavior, how the spiders behave, how the web formation happens, everything including the vibrations, all of this is evaluated into this algorithm. This For starting with uh, development, it was introduced to solve global optimization. Foundation is based on the web formation of the spiders along with the pheromone distribution. The strategy is mimics a cooperation. Moving on to the next slide, that is biological inspiration. Yeah, we have spider web. The spider web are nothing but the web formation by the all the spiders that actually evaluates to the space and the search space. The web represents the search space. The vibration here also mimics the communication between the spiders. These are very useful for signal transformation, for information sharing and attraction. And pheromones, these are the chemical signals guiding exploration and used for marking good areas in the search space. These are all about biological inspiration. Again, we know the gender roles. The whole territory is divided into female and male mates. Thereby, we evaluate the fitness and everything. Moving on to the next slide, we have the core components. Here, the spiders are nothing but the agents, where each spider is evaluated to an agent through which we also calculate the fitness and everything. Population of candidate solution with fitness values and position coordinates. Web structures, as I've mentioned earlier, web structures is completely useful for to evaluate the search space. So it's a hyper dimensional space mapping to problem variables, that is nothing but this evaluated for search space. And vibrations are nothing but the signals transmission for information and sharing and attraction. And then moving on to the next slide, we have how SSA works. The first part one for this SSA algorithm, that is a social spider algorithm, we have initialization phase, where first thing we do is initialize, that is generate n random spider positions x1, x2, x3 into xn in the d dimension search space. Now the second step is evaluating fitness. With a given formula, we evaluate the fitness, that is calculate xi for each position. Identify best solution x best. Next, distance matrix. Compute the Euclidean distance between the spider. We also evaluate the distance by using the distance formula. This is all about an iteration set, and then we also formulate with the iterations, which is alpha, beta, and delta. Moving on, Amog will be taking over with the next slides.
I'll be explaining the mathematical principles. So the vibration intensity indicates that how stronger each spider are close to, and the attraction indicates vibration decay with distance or closer spider influence with each other's movement. Movement equation. This equation guides how spider move towards neighbor or the global west or to explore the global west. Use of parameters like alpha, beta, and delta. Alpha indicates inertia, and beta indicates attraction to the global best, and delta indicates random exploration. Moving on to the next slide. How SSA works. So in this slide, we have shown that how SSA works. So neighbor detection tells us that each spider identifies the closest neighbor using the distance matrix as explained by Arushi. The weighted movement combines attraction towards nearest neighbor, the global best, and the random movement for exploration. Boundary handling. If updated position go outside limit, they are corrected to stay within feasible boundaries. And the fitness update tells us that after moving, each spider calculates a new fitness value and updates the global best solution for a better and easy calculation of the matrix. Moving to next one. How SSA works using convergence. There are mainly four points in this: iteration loop, the diversity checker, termination, and the linear decay. Iteration loop, the algorithm runs from T1 to N. In every iteration, all spider updates their position using vibration signal, neighborhood influence, and the global best attraction. This is repeated updating gradually, which improves the solution. The parameter decay. Using the alpha and delta values, higher the exploration in early stages, higher is the possibility of finding the global best. Diversity checker. The algorithm checks whether the population of spider has become too similar. If the standard deviation of the position is below threshold, it means the swarm is losing diversity and might get stuck in a local minima. Or SSA applies a algorithm to some spiders to reinforce and find a better solution to find a global best. Termination condition. The algorithm stops when one of the following is true, like maximum iteration T is reached, the algorithm stops, or global best solution is reached, the algorithm is stopped. Linear decay of alpha. The algorithm reduces alpha linearly using alpha is equals to t minus t by 0. As t increases, alpha decreases smoothly. Uh, okay, next slide.
So I'll be
Abhijna is going to continue with it.
Yeah. Here's a benchmark example using Rashtrigan's function, which is a tough multimodal landscape with lots of local minima. Here, each spider represents an XY coordinate in a 2D space, and the goal here is to reach the global minima, which is present at the origin. SSA works well here because vibration helps the swarm to move towards the promising region instead of getting stuck. In experiments, SSA converges 5 to 10 times faster than GA and 2 to 3 times faster than PSO algorithm, with over 95% success rate within 500 iterations. Next, we are comparing the performance with other algorithms such as PSO and GA. SSA is simpler to tune because it uses fewer parameters. It explores search space and more effectively and reaches good solutions faster, even with smaller populations. Compared to PSO and GA, SSA escapes local minima better due to vibration-based communication, and it performs reliably in both continuous and discrete problems, even at higher dimensions. Uh, the real world engineering applications of SSAR in mechanical design, it reduces structural weight under stress limits. In logistics, it is used to solve the routing problems like TSP. In machine learning, it is used to train neural networks and SVMs. In electrical and civil engineering, it is used for power flow and energy dispatch and for structural design. And in robotics, it helps coordinate forms and avoid collision. Here's a case study in traveling salesman problem. In traveling salesman problem, each spider represents a full route and fitness in total distance. Because strong solutions send stronger vibration, the swarm quickly gravitates towards the good routes. For 50 CT TSP, SSA reaches near optimal solution in under 2 seconds, while GA usually takes 8 to 10 seconds and produces weaker results. This gives real world benefits like 15 to 25% fuel savings in network delivery. Uh, in conclusion, SSA is a robust global optimizer with strong balance between exploration and exploitation. It is already being used in supply chain optimization and engineering design. Uh, Future direction includes hybrid SSA ML models and GPU based parallel versions and quantum inspired variants. Long-term goal is to make nature-inspired algorithm the standard engineering tools by 2030. Thank you all.